because I know sound is like it's the most common wave. You know, when you think of a wave, again, when you hear wave, a big thing that you think about is sound waves.
Sound waves. So when you hear a sound wave, think about how insane. We were talking about this the other day about how crazy sound waves were. So essentially, you're hearing a noise, and to your brain, that's just like you hear a noise and you're like, okay, whatever. But what's actually happening? Let's think about this.
Mm-hmm.
Your eardrum is vibrating back and forth. And what's making it vibrate? Well, it's the sound wave. Well, what is the sound wave? So a sound wave is just through the air molecules are going back and forth because the source of the sound creates high pressure and low pressure areas in the air.
Yeah.
And so the high pressure and low pressure areas is what pushes back and forth the air molecules, and that propagates through the air and then reaches your eardrum. And your eardrum literally vibrates to the tune of the high and low pressure. I'm making a movement with my hand if you're listening on Spotify or whatever. But your eardrums are going back and forth at the same exact rate that the air is vibrating. And your brain, in turn, translates that into a noise. Now, it is a lot more intricate than just that, because you wanted to talk about like what makes a sound different.
Yeah, that in a second. But I wanted to continue on your whole discussion about how it vibrates and then your ear vibrates at that. And that is, in the essence of it, the fundamental reason why sound exists, and that's vibrations, right? So everything in the world vibrates. We are vibrating right now. We're giving off infrared radiation that would not be sound. But
very true.
Everything in the world has a natural frequency. This is your lowest resonant frequency, and we can maybe get into it in a second. But everything has a natural frequency, the frequency at which it vibrates. Now, if you happen to disturb this body, now when I say disturb, it's like you can hit it, you can pluck it for a string. Very many things. I'm just thinking about, well, and anything if you're just hitting something, right? That's the easiest way to think about it. If you disturb it, what's actually happening is, for a sound to occur, you're first hitting it at that lowest resonant frequency. So you're vibrating it at the speed that it itself vibrates, and it creates a sound. Because what's again happening is lower vibrations would not register in your ear, but higher vibrations would basically cause the molecules in whatever you're hitting again to vibrate with that same sound. So the moment you hit it, the vibration in the air around it is actually what's causing the sound. Because when something is stationary, again, no sound is being created. But when it's hit or something like that, there are pressure columns, as you were talking about, in air that get sucked in and sucked out. This is compression and rarefaction columns. Yep. So compression columns are dense air columns. Rarefaction columns are less dense air columns. And this less dense, more dense, because these molecules from the item itself are vibrating, it vibrates this pressure. This pressure is now moving back and forth at the same speed of the vibration.
But here's why, though. If you think about it, imagine you have, like, this is just like pressure in general. If you have a high pressure area, like let's say the inside of a balloon, and then you let go, or you open a hole, the high pressure air is going to move towards the low pressure air. So what actually makes the sound travel through the air is that, okay, you have a high pressure, low pressure, high pressure, low pressure, and the air is constantly moving from high pressure to low pressure. But as the air moves, it leaves behind a low pressure area. And so it moves back and then forth and back and forth. And that's what creates the vibration. And then, you know, of course, the air molecules are touching each other. And so if one moves, or if like one column moves, then it pushes the rest of it. And that's what causes sound to just go across the air.
And that is why when you just hold, for example, a string, and you just hit it, and even if you hold it tight and you just hit it, probably you won't hear anything loud. Do the same thing on a guitar. It's a whole sound. And again, the reason this is happening is simply because more things are vibrating. So there's that whole what's it called? I don't know what it's called, but like the, you know, like the wooden part of the acoustic guitar. You know
the
what
body?
I guess, yeah, the body of the guitar. So the moment the string is plucked, I'm just thinking of a guitar as an easy example. When you have a string, just nothing there with it, just air around it, and you pluck it, the air around it, there's just a little bit of that's vibrating. That then gives you a little bit of sound. Maybe you hear that tick, tick, you know what I mean, when you stretch a string and you try to hit it. But then in a guitar, the same vibrations is now sent through the whole body of the guitar. So this is actually also a thing of resonance. This is where resonance comes from. What happens is the body of the guitar vibrates at the frequency of the string. Wherever you are playing the particular string, the body is now vibrating at that frequency. And because the whole body with the air around it is now vibrating at that frequency, you hear it a lot louder. It amplifies is the easiest way to think about it, because literally what happens in the wave is the amplitude increases. Nothing else changes, obviously, because the pitch and everything is the same, but the amplitude increases. So they're all, and it's the same thing even with like a tuning fork, and you put it in like a box, and it just all of a sudden, whoa, you just hear this crazy loud noise. It's all again about how many things are vibrating and how these vibrations are sent through to other objects. A simple, or another example of this would be, and this is quite common, when you I don't know, is this a common physics experiment, when like you have like I'm just going to say it, like the two tuning forks, for example, or something like that, like two things together, and you ring one of them, and then after a second you stop ringing one of them and the other one starts ringing, and that's basically resonance for you.
Well, it's not that it starts ringing, it's that causes...
That's what I'm trying to say, right? Okay. So that was the point that I was trying to make. So what's actually happening is, because they both have the same natural frequency, because they're the same object, when one starts vibrating and making a sound, so does the other, because they have the same natural frequency, and they start hitting, and that one starts vibrating too, and boom, it's magic. But no, it's just physics.